Today, we are diving into what might be the single most powerful idea in all of science. We're getting this straight from the mind of the great physicist Richard Feynman. And it's a concept that really underpins everything. It all starts with a huge, kind of world-ending question. Okay, so just imagine for a second a total cataclysm. Every book, every server, all of our scientific knowledge, poof, it's gone. And you get to pass on just one single sentence to whoever comes next. What's the one thing you could tell them that would give them the biggest possible head start in rediscovering how the world actually works? This is the exact thought experiment that Richard Feynman loved to pose.
And this was his answer: the atomic hypothesis. Feynman was convinced that this one sentence contains an unbelievable amount of information. It's like the master key that can unlock the secrets of our entire physical reality. So, let's go ahead and use that key. Let's see what we can open up. Now, to really see just how powerful this idea is, we're going to start with Feynman's favorite example, a simple drop of water. Just imagine we have a microscope so powerful it can see the things we thought were unseeable.
You know, when you look at a drop of water, it looks perfectly smooth, right? Continuous. But if we could zoom in, say 1 billion times, that picture would completely shatter. What you'd see is this chaotic, teeming world of jiggling particles, just constantly bouncing and tumbling all over one another. This is the world of atoms. So just how small are we talking? Well, their diameter is about 10 to the minus 8 centimeters. That's 1/100 millionth of a centimeter. I mean, that number is so small, it's almost meaningless by itself. So let's try an analogy to really get our heads around it.
Let this one sink in for a second. Okay, picture an apple. Got it? Now, imagine that apple growing and swelling up until it's as big as the entire planet Earth. An atom inside that giant Earth-sized apple would be about the size of the original apple you started with. That's the absolutely mind-boggling scale we're dealing with here. And it's this constant motion that explains the different states of matter. So in ice, the atoms are all locked up in this rigid, crystal-like pattern. They're like dancers holding their positions, just kind of vibrating in place. But then you add some heat, right? They break loose, and now you have a liquid. They can jiggle and slide past each other. Add even more heat, and they just fly apart completely, and that's steam. It's the same atoms, just with different amounts of jiggle. So you see, the atomic hypothesis isn't just some static picture of reality. It's a dynamic key. It helps us explain the world we actually experience every single day. Let's look at a few examples. Have you ever actually wondered why blowing on your soup works? I mean, why it cools it down? Well, it's all about atoms. The little molecules in your soup are all jiggling around at different speeds. The ones at the surface, the fastest and most energetic ones, can get knocked right out of the liquid. They escape as vapor. And because these little escapees take an extra big chunk of heat energy with them, the average energy of all the molecules left behind goes down. And that means your soup gets cooler. It's evaporative cooling in action. Okay, but what if you put a lid on that soup? Or just, say, a cover on a glass of water? Molecules are still evaporating from the surface, sure, but now the molecules in the air above are also splashing back down into the liquid. And eventually, you hit a point where the rate of leaving is exactly the same as the rate of returning. To us, it looks like nothing's happening, but at the atomic level, there's this constant, furious exchange going on. That's what we call dynamic equilibrium. And the same idea applies when you dissolve salt in water. To our eyes, it just looks like the salt disappears. But really, it's another one of these dynamic processes. You have salt ions constantly breaking away from the crystal and floating off into the water, while at the very same time, other ions are bumping back into the crystal and rejoining it. It's a two-way street. And this concept, it scales all the way up to something like a chemical reaction. A reaction is really nothing more than atoms rearranging themselves. They're just changing partners. Think about a fire. When you burn charcoal, all that's happening is carbon atoms are letting go of each other to link up with oxygen atoms from the air. And that simple act, that rearrangement, is what releases the incredible amount of energy we see as light and feel as heat. Okay, so this brings us to the truly profound part. We've seen how atoms can explain the physical and chemical world, but this idea, it goes so much further. It goes all the way to explaining us. Now, you might be thinking, Okay, this is a great story, but how do we know it's actually true? We can't just see an atom with our eyes, but we can see their effects everywhere. We see it in what's called Brownian motion, that weird random jiggling of a speck of dust in water. What's causing that? It's being bombarded by billions of invisible water molecules. We also see it in the perfect, sharp angles of crystals, which form exactly like our models of stacked up atoms predict they should. This isn't just a guess anymore. It's a reality. And here's where it gets really staggering. Feynman called this the most important hypothesis in all of biology. The idea that everything animals, and yeah, that includes us, everything we do is ultimately just atoms doing what atoms do, following the known laws of physics.
I mean, that is a profoundly unifying idea. It suggests there's no magic wall between the living and the non-living worlds. Everything from a thought to a feeling to moving a muscle is, at its very core, the result of atoms interacting with each other. It's just they're arranged in these fantastically complex patterns.
So I'm going to leave you with this final, truly awe-inspiring thought from Feynman. The next time you look in a mirror, or you just look down at your own hand, I want you to consider what you're really looking at. A great glob of these atoms, arranged in a pattern so complex, so intricate, that it can do something absolutely astonishing. It can wonder about itself. Thanks for joining.